In order to plug 0 in, that x has to go away, so it has to cancel, has to get out of there. So what something we can do? Algebraic manipulation.
You can square both sides.
There's no two sides to this. You can only multiply this thing by a form of 1 if you wanted to. You can multiply by a form of 1. Squaring it is not something you can do.
Square root of 3 plus x.
So you want to do square root of 3 plus x, yep.
Over.
Plus. Over what?
Over the same thing.
3 plus x plus root 3. It's kind of like a conjugate. You've done stuff like this before. Now, you test this, and you might be right. You might be wrong. There might be something slightly different. But if you multiply this out, you end up with 3 plus x plus root 3 plus x minus root 3 plus x minus what? 3 all over x times root 3 plus x plus root 3. What happens on the top? This cancels, right? This whole thing cancels, and what are you left with? You have the limit as x goes to 0 of x over x times root 3 plus x plus root 3. What cancels now? The x is canceled. Is that exactly what you were looking for? So this limit is now the same. You end up with 1 over the square root of 3 plus x plus root 3. What do you end up with? 1 over 2 root 3. And if you wanted to rationalize the denominator, which you don't absolutely have to do, you end up with root 3 over 6. There it is. This is kind of just a cheap trick. That's it. You do the table set, and we want to start at, let's say, you're going to let's go to, I don't know, negative 0.5, and what's delta going to be? 0.1. And you do the table, and look what you get. Should there be an error right there? Yeah, because you can't divide by 0. So what does that table tell us? If you're approaching from the left and the right, does it look like it's approaching the same thing from the left and the right? Yeah, it looks like it right here. Looks like it's approaching the same thing. So you know that you're from this table, you're guessing that the limit as x goes to 0 of f of x is less than 0.29112, and it's greater than what? 0.28631. It's between those two. This is a table right here. That is a table. So you can have a graph and look at a picture, right? So here's the thing. We now want to solve this equation. 3x squared plus ax plus a plus 3 has to equal x plus 2 times something, right? Something. Now if you want to isolate the question mark, what do you divide both sides by? So you have question mark is equal to 3x squared plus ax plus a plus 3 all over x plus 2. How do you go about simplifying that? You want to factor the numerator, that's correct, but how are you going to go about doing that? You've done this before. I'll start typing it slowly. Yeah, they call it long division. We can just call it a polynomial division. You're doing x plus 2 into 3x squared plus ax plus a plus 3. What part of that polynomial underneath this is the radicand? What part of that is the constant? And? So what's the constant? A plus 3. What's the leading term here? What's the leading term? So it's 3x squared over the leading term right there, which is, what's the 3x? You multiply now. 3x squared plus 6x, and now you. What's 3x squared minus x squared? 3x squared. I mean, these cancel, and you're left with a minus 6x. Is that correct? Mm-hmm. What do we drop down? You can drop down a plus 3. That's fine. What's the leading term now? It's a minus 6 times x all over the same leading coefficient. What's that come out to be? Plus a minus 6. You now multiply a minus 6 times this thing, and what do you end up with? A minus 6 times x plus what? 2 times a minus 6. And what do you do now? Subtract. If we subtract this, we have 1a and 2a's, and you subtract. What's 1 minus 2?
1 minus 2 is negative 1.
So negative a. And what's 3 minus negative 12? 3 minus negative 12 is 15. For this to divide evenly, what should this be? That should be 0. So you know that negative a plus 15 has to be So a is equal to 15. How can you test this? You can plug it back in, right? You get 3x squared plus 15x plus, what's 15 plus 3? That's 3 times x squared plus 5x plus 6. What's that turn into? X plus 2 times, and what do you magically have now? You have that term. Now the question asks, if so, find the value of a and the value of the limit. We can now find the value of the limit because now we know that the limit as x goes to 0, it's going to be 3 times x plus 2 times x plus 3. Remember, this is when a is equal to 15 all over x plus 2. What is it? X minus 1, I think. Was that it? Was it x minus 1? Yeah. What cancels? The x plus 2's cancel, so you're left with a limit as x goes to 0 of 3 times x plus 3 all over. So what's that equal to? 9 over negative 1 is negative 9. Here it is, polynomial long division coming back and actually being helpful. Imagine that. It's continuous at a number a if the limit as you approach from both sides, if the limit as you go to a is the function evaluated at that a value. So what does this mean? F of a has to be defined. So if the function isn't defined at that value, can it be continuous there? No. The limit has to exist, so if the limit doesn't exist, it doesn't work. And the limit has to equal the function value. So what does this look like? What cannot be continuous? So let's say there's just an open dot, and here's x equals a. Is it continuous at x equals a? No, because f of a is not defined. There's number 1. What about this? It's open there, here, and it's open like this. Is the function defined at x equals a?
No.
Yes, it is. It's defined right there. Is the function defined at x equals a? Yes. But is it continuous?
No.
No, because the limit does not exist, because it's different going from left to right. And then for the third one, so here's 2, the limit has to equal the function value. So for example, let's say I had an open dot like this, and it was up here. This is number 3. Does the limit exist? Yes. The limit exists. It's going to here and here. It's getting infinitely close to that dot. Does the function exist at x equals a? Yeah. But is it continuous at x equals a? No, because the limit and the function value at that value have to be the same. They have to be the same. So for each of these are not continuous. Here are the examples of the ways you can violate continuity. Not continuous. You know, for tan inverse, the domain is all real numbers. That's what I like ARN. What about ln? It's x greater than 0, right? And because of this, what do we know? X cannot equal negative 1 or 1. So the domain is going to be x such that x is greater than 0, but x can't be equal to
1.
We already took care of the negative 1 thing because x is already positive. There it is. So that's the domain. You've glued it together with legal operations with continuous functions. So therefore, this is the domain. So this is where f of x is what? Continuous. Does that make sense, everybody? Yay, very good. You spend a lot of time solving for zeros, right? Factoring and setting equal to 0. Are there functions that are really, really, really hard to factor or basically impossible to factor? Absolutely. Well, let's say you kept on testing and you found that this is negative and that's positive. So what has to exist somewhere in between?
0.
A 0. Pick the value in between. Let's say this is negative. So where does the 0 have to be? Somewhere between. So this is point A, this is x value B, and not B, this is C. Let's say I test x value of A and x value of C. One is negative, one is positive. What should I test next?
0. Put it in.
The one in between. Test the B value, the one in between. Let's say that one was negative. So where do we know the 0 has to be? Between what? So let's say I chose the one halfway through, and we call this one D, and this one came out to be positive. So where does the 0 have to exist? Between B and D. Well, let's say I chose this one and made it E, and it turned out to be negative. Well, we're still in B and D, but what do we test now? You test over here. You can get closer and closer and closer. This is an algorithm for finding zeros, where all you need to do is evaluate. All you need to do is evaluate. Can a calculator do this pretty quickly? Yes. Is this actually how the calculator does it? No. There's a quicker algorithm. The calculator's been programmed a little bit better than this, but this goes pretty quickly. All you have to do is be able to evaluate the function. But it has to be closed, has to be a closed interval, and has to be continuous on that closed interval. Does that make sense, everybody?
More than 1 0.
There might be more than one, yes. You might have more than one, absolutely.